Good afternoon, everyone. Today we will discuss about reduction reactions of aldehyde and ketones. Yeah. Previously, we have discussed about nucleophilic addition reactions of aldehydes and ketone using various reactants with elimination of water as well without elimination of water. So, as we know, aldehydes and ketones can undergo reduction reaction to give different products under different conditions. So let's look at this example. In this, I have chosen simple aldehyde, then R group may be any alkyl group, if propyl, methyl, ethyl, phenyl, either any group R may be. Clear? So when it is subjected to undergo reduction in the presence of hydrogen, when we are using hydrogen, molecular hydrogen, always we used catalyst out of these nickel, platinum, and platinum because catalyst is used for the adsorption of hydrogen gas on the surface as hydrogen gas is lighter in nature. So suppose there is a catalyst. This is the surface of catalyst and the molecules of hydrogen will get trapped on the surface of catalyst so that these do not escape from here and can further react to a reactant that is aldehyde. Okay. So upon its reaction with aldehyde, it gives primary alcohol. Means one hydrogen is added to this carbon and the second hydrogen is added to this oxygen. And there is formation of a bond between oxygen and hydrogen and this carbon and hydrogen. So we get primary alcohol. So look at some other examples. The simple aldehyde is formaldehyde in the presence of nickel, either nickel, platinum or palladium. You will get methyl alcohol. The next is acetaldehyde. In this case, this aldehyde group get reduced. You will get the product ethanol. Yeah. So when we are using the reactant as aldehyde, always we will get primary alcohols. Yeah. Okay. The next is acetone. Acetone, this is a ketone. When it is subjected to react with molecular hydrogen in the presence of catalyst nickel, then this carbon will get hydrogenated. So as CH, and this oxygen will also hydrogenated as OH. Then what kind of product we will get? That is secondary alcohol. So as this alcohol is attached to the carbon which bears two alkyl groups, that's why it is called as secondary alcohol. So the reduction reactions are carried out either catalytically with the hydrogen in the presence of nickel, platinum, or palladium. Or either these reactions can also be conducted using other reagents such as lithium aluminium hydride and sodium borohydride. So these are the reagents which also provide or give the reduction reactions. But how these reagents cause reduction? So for this, look at the mechanism. First of all, what is the structure of lithium aluminium hydride? Okay. This is your lithium aluminium hydride. In the aluminum is tetracoordinated, that is attached to 4 hydrogens. That's why tetracoordinated. And it is in this salt form, and aluminum have negative charge as it is attached with lithium positive. Lithium is electropositive in nature, so it will lose its electron, and there is positive charge on lithium. Yeah. Similarly, the another reagent is sodium borohydride. The boron is also tetrahedral in this structure because it is attached to 4 hydrogens, and there is a negative charge on boron and the positive charge on the sodium, as sodium is electropositive in nature. So both of these reagents give H negative. So these are the source of H negative. H negative further will be added to any of aldehyde or ketone. Thus, you will get the primary and secondary alcohols. Clear? So look at the mechanism. This H negative is coming from this aluminium hydride here. So you can directly attack, like here, H negative will attack on this carbonyl center because this carbonyl center is electrophilic in nature, and H negative here is acting as a nucleophile. On other hand, this oxygen will be coordinated to lithium positive, as lithium has the same positive charge I have already told to you. So what is happening next? There is formation of a tetrahedral intermediate. When this H negative will attack, then there will be shifting of pi electron toward oxygen. Then the oxygen will get negative charge, and you will obtain tetrahedral intermediate. Okay, so with the formation of this tetrahedral intermediate, you will get also aluminium hydride, AlH3, as byproduct. Again, as if we simplify the mechanism again, then at the end of workup, we add water. When we add water, there is transfer of H positive ion. When H positive ions are transferred, so this O negative will get protonated, and then you will get the alcohol, plus there is regeneration of lithium aluminium hydride. Okay. So the second step, I have not told to you this step because in this phase there is development of bond between oxygen and aluminium, which regenerates the catalyst, because oxygen is here acting as a nucleophile. It is a hard nucleophile, so it will attack easily on the aluminium. Then when there is formation of bond between oxygen and aluminium, then of course lithium is positively charged. Aluminium will accept the there will be negative charge on the aluminium. So when water is added, it will get the lithium aluminum hydride as again new reagent. So here is the regeneration of lithium aluminum hydride. But you have to add water to get this protonated product. So don't forget to add water in the reaction when you are using lithium aluminum hydride or sodium borohydride. Always in such kind of reaction, you will see the first reagent is your lithium aluminum hydride, and the second will be water. So lithium aluminum hydride or sodium borohydride are the sources of H negative ion. Then you will get this tetrahedral intermediate. Then upon addition of water, you will get your final product as alcohol. Okay. Then if I summarize this reaction, when we are using hydrogen, molecular hydrogen, to conduct reduction, either sodium borohydride or lithium aluminum hydride, then always the aldehyde will give the primary alcohol as a product, and when the reactant ketone is used, it will give you the secondary alcohols. Yeah. So this was the reduction reaction of aldehydes and ketone in the presence of catalyst, and these reagent, that is reduction to alcohol. So major product formed in this reaction is alcohol. And you can solve this in the some typical exams where there are options are given in which there is also product like alkanes are also formed from aldehyde and ketone, but in these reactions the major product is alcohol. Okay. Look, this is some other kind of reaction that is known as Mirwin-Pondorf-Verlet reduction. Okay. So in this reaction, what is happening? This is your ketone in which there are two R groups. One is R, another one is R1. Okay. This reaction is subjected in the presence of metal oxide, that is aluminium isopropoxide. You have chosen aluminium isopropoxide, and the solvent you are choosing is isopropanol. Always you should choose the aluminium salt, the aluminium product, aluminum oxide you can say, and the solvent that should be same. Like there are three carbons in the this aluminum oxide, that is prop, isopropoxide. Similarly, the solvent we have been taken is isopropanol. So what is the structure of aluminum isopropoxide? So this is the structure of aluminum isopropoxide. It is tri-coordinated, in which aluminum is linked to oxygen, then it is linked to carbon and to methyl group. This is your isopropyl group. You can say isopropanol group. Yeah. Okay. And simply the what is isopropanol? Iso, in which the OH group is attached to second carbon, that is known as isopropanol. 1, 2, 3. It is its isopac name is also propane 2-ol. Clear? This is also known as propane 2-ol, and its common name is isopropanol. So what is the advantage of this reaction? In this reaction, if you are using particular ketone, this ketone will get converted into alcohol. Clear? And the solvent you have been choosing here is isopropanol. It will get converted into the ketone. So it is vice versa. Ketone will get converted into alcohol as your product, and the alcohol means your solvent, that is isopropanol. It will get converted into ketone. So you can obtain desired kind of alcohol in this reaction by choosing particular ketone. So look at the mechanism. Yeah. So just a sec. Hmm. So Mirwin-Pondorf-Verlet reduction reaction. In this reaction, there is hydride shift. You have to remember this point. Hydride shift will occur in this reaction. So this mechanism is believed to go through a catalytic cycle involving a six-membered ring as transition state. So I will let you know how six-member transition state is formed in this reaction. So the first is, this is the green color. This represents your aluminium alkoxides. This is your starting material. Okay. And this is your ketone. It is your reactant. So when they both react, what happens? As we know, oxygen have tendency to form the bond with aluminium. So it will interact with the aluminium when it will interact with the aluminium. So what is happening next? I will just make the transition state. Transition state is the state in which we show with the bonds which are formed and the bond which are breaking. Okay. So in short, aluminium, oxygen, C. And there are two groups, R1, R2, oxygen, R C, R1, R2, oxygen, C, R1, R2, and H is here, and C double bond O, R3, R4. This hydrogen will interact with the carbon and this oxygen will form the bond with aluminium and these two bonds will get broken. So I will also represent it with dotted lines so that you can see. Yeah. So just count the number of atoms. I will use another marker to variate it from the this molecule so that you can't be confused. One, two, like this. One, two, three, four, five, six. Yeah. So here is the formation of a six-membered ring. In more clear manner, I will let you know. Yeah, just O, C. There are two groups and H, C, O, R3, R4, R1, R2. Now, you can see it clearly now. This is your six-membered ring. So this is your transition state in which you are seeing that in what kind of bonds are new bonds are formed and the old bonds are breaking. So the previously there is it is your tri-coordinated complex, the aluminum oxide is okay. During transition state, uh, you get tetra-coordinated aluminum. In this, aluminum is linked to four ligands, like 1, 2, 3, 4. It is linked to four oxygen. That's why it is called as tetra-coordinated. Yeah. So, and in this tetra-coordinated aluminum, there is a six-member ring which is your transition state. So as this is transition state, just represent it in the square brackets. Yeah. Okay. So the next step is transfer of hydride group. So the H negative from here will be transferred from this carbon to the carbon which bears carbonyl group. So when H negative will attack on this electrophilic center, then these pi electron will shift it toward aluminium and the bond between this aluminium and oxygen will also be shifted towards this carbon oxygen single bond. So what you will get, you will get this as ketone R1 R2 C double bond O. Yeah. R1 R2 C double bond O. You can see clearly the molecule attached to this aluminium is converted into the ketone. and this ketone get attached with this aluminium oxide, which is tri-coordinated in nature. Now, the next is the role of solvent, that is alcohol. You are using isopropanol here. Okay. So this isopropanol will exchange its H positive with it, and this oxygen will again attack on the aluminium. Then you will get this as alcohol. Okay. Again, in this reaction, aluminium isopropoxide is regenerated. Okay. And plus tri-coordinated aluminium is obtained. OCCH. So what we see, the ketone is converted into alcohol and the alcohol is converted into the ketone. So by varying the R groups, you can choose any kind of reactant and obtain the particular product. So this is highly chemoselectivity. So by this, you can obtain the product there. Those are chemoselective. So this is the purpose of Mirwin-Pondorf reaction, to use these condition as aluminum oxide and isopropanol as reagent and solvent. Clear? Okay. Then next is third one is reduction to pinacols. Now, what is the word pinacols? Here we have been using the word pinacol. When two OH groups, alcoholic groups, are present on the adjacent carbon, like this. This is your carbon number 1, carbon number 2. The carbon number 1 also bears OH group and carbon number 2 also bears OH group. Then this product will be named as pinacols. Clear? Okay. In this reaction, two molecules of ketone are reacting. There are two molecules of ketone. Okay. And this reaction is carried out in the presence of magnesium amalgam. When any metal is linked to mercury, there is bond between a metal and mercury, then that is known as amalgam, and that metal amalgam. Here the metal used is magnesium, that's why it is called as magnesium amalgam. As well, in the last step we have been using water also. So then you will get the product as pinacol. There is formation of a bond between these two carbon, and this oxygen will get reduced to form OH. So by which mechanism pinacols are formed? And magnesium is here acting as the electron donor. It has two electrons and it will donate its electron to this oxygen. Means it is forming the bond with this oxygen. And here is the pi bond. So if we do homolytic fission means when there is bond between two atoms, their electrons get transferred like this way. Oxygen gets its own electron and the carbon gets its own electron. Both get one electron. The bond is broken from the center. So that fission is known as homolytic fission. And after homolytic fission, both the atoms have one electron. When the atoms have electrons like these are known as radicals. Yeah. If an atom gets positive charge, then it is cation. If the atom gets negative charge, it is anion. But if an atom gets an unpaired electron after homolytic fission, then you will call it as radical. So here there is a bond formation between, like, magnesium is electron donor. Just this is your one electron of carbon, another electron of oxygen. So one electron of magnesium is pairing with this pi electron of oxygen. When the magnesium will pair with oxygen, the magnesium will left with one electron, and this carbon will also left with one electron. So this is known as ketyl radical anion, as there are two unpaired electron, two unpaired radicals. So that's why we call it anion also. So this is your ketyl. The term we are using term is ketyl. This is your intermediate in the form of radicals. Clear? Okay. Now, the second molecule will approach this ketyl intermediate when this second molecule will approach. Similarly, as in first step, the magnesium approaches the oxygen and pair up with the oxygen. The magnesium will also pair up with the pi electrons of oxygen. And always remember, when we represent homolytic fission, we use half-headed arrow like this. Clear? Okay. When the second molecule is pairing with the magnesium, then you will get this adduct in which magnesium is coordinated to two oxygen atoms, as magnesium has a valency of 2. Now, these two carbon carries a radical. Each carbon carries this radical. These radicals will also get paired up, and you will get a carbon-carbon single bond upon pairing. Okay. Now we have also used the water in this reaction. Upon addition of water, what is going on? This five-membered cyclic compound. This is five-membered cyclic compound. Mm, okay. This will get broken from here, and the oxygen will get protonated, and magnesium will be attached to two hydroxy groups as magnesium hydroxide. You can write like this MgOH2, and this is your diol. So this is known as pinacol. In this, the OH groups are present to adjacent carbon. So by this way, you can also form pinacol, but the condition is the reagent you are using is metal amalgam and water. Clear? Okay. Um, the next is just we have done with the example in which there is formation of alcohol as a product from both aldehyde and as well from ketone. Clear? Now, look at the reaction in which the aldehyde and ketones are converted into hydrocarbons. So, it can be obtained under several conditions and particular reagent. So, what kind of particular reagent is used to obtain the hydrocarbon as major product? So simply this is your aldehyde. In this, the reagent used is zinc amalgam in the presence of HCl. Then this CHO group will be reduced to CH3. Means this carbon is also hydrogenated and this oxygen is also hydrogenated. So just look at this one also. These are the four molecule of nascent hydrogen. Now, what is the nascent hydrogen? Nascent hydrogen is the newly born hydrogen. Newly born hydrogen. This is not like as a hydrogen molecule. So this is individual atom when hydrogen is uh, homolytically cleaved, then it form hydrogen atom. This hydrogen atom is very reactive, and so it is represented in the brackets. So that's why it is called as nascent hydrogen, as this hydrogen is producing in situ reaction. In reaction it is producing, and it is not escaping the reaction. So it is a part of the reaction. And the source of nascent hydrogen is HCl. When you are using zinc amalgam plus HCl, it will provide you four nascent atoms. Yeah. So here the molecules will be more, the four molecule of HCl. So it depends on the how many number of molecules we have been using the HCl. Yeah. And further there is formation of zinc chloride. So to get two nascent hydrogen, two molecule of HCl will react with zinc amalgam, and you will get zinc chloride plus two nascent hydrogens. So this is the purpose of using zinc amalgam in the reaction. Similarly, when ketone is subjected to react with zinc amalgam in the presence of HCl, then this CO will be converted into CH2. Carbon is hydrogenated again with the removal of this oxygen, that is water. Then the next example is acetophenone. This is your acetophenone. Again, you are getting the product. This carbonyl group is reduced to CH2 group, that is ethyl benzene. So Clemmensen reaction is used for those aldehydes and ketones which are sensitive towards alkalis. Yeah. So alkalis are like sodium metals, magnesium, these are alkalis. If when these are sensitive towards these alkalis, we will use such kind of reagent like zinc amalgam and HCl to obtain the desired product as hydrocarbons. The next one reaction is Wolff-Kishner reaction. The Wolff-Kishner reaction, the reagent used is hydrazine. We have already done with the reactions of carbonyl compound with hydrazine, and the product we got is hydrazone. Hydrazone, this is your hydrazone, in which there is formation of a double bond between carbon and nitrogen with the elimination of one molecule of water. Okay, now further this hydrazine is followed by the reaction with KOH in the presence of solvent glycol at high temperature, that is 453 to 473 Kelvin. So it's a temperature up to 180 degrees Celsius to like 200 degrees Celsius. Then you will get the alkane as product. This CH group will be hydrogenated, and with the evolvement of, with the formation of nitrogen. Yeah. As this NNH2 group will be released as N2. But remember, you need to use high temperature to conduct this reaction only in the presence of glycol and potassium hydroxide. So in both reaction, Clemmensen reduction and Wolff-Kishner reduction, you are getting the finally product is alkane, that is hydrocarbon. But what is the difference? The first is the in case of Clemmensen, obviously, which are only those aldehydes and ketones are used in this reaction which are sensitive to alkalis. And in case of Wolff-Kishner reactions, only those carbonyl compounds will be used which are sensitive to H positive, which are sensitive to acids. Yeah. As in Clemmensen reduction, we are using HCl, means HCl can break down the molecule. That's why we are not using that one in Wolff-Kishner reduction. So Wolff-Kishner reduction is done by using some different reagents, that is hydrogen. Clear? Okay. So the next is reaction with hydrogen iodide using red phosphorus. So where red phosphorus is used in our basic life, the matchstick we use, it is coated with red phosphorus, the salt on matchstick, uh, which produce fire that is known as red phosphorus. Here, okay. So when it is subjected to react with hydrogen iodide at temperature 423 Kelvin, and you again this your H group will be reduced to CH3 group. Okay, this is your acetone. This is aldehyde. Aldehyde will also giving alkane, and ketone. This is also converted into your alkane. That is propane, and this is your ethane with the elimination of water and iodine. Okay. So first of all, these aldehydes and ketones are converted into their uh, respective alcohols. Then this OH group is eliminated upon as water molecule. Upon elimination, it forms the carbocation. Okay. Thus, the reaction of phosphorus and HI produce I negative as nucleophile. This nucleophile, it will attack on the carbocation. Then there is formation of bond between carbon and iodine. So this is your intermediate in which there is the bond between carbon and iodine. So this is iodated propane, isopropane, you can say. Clear? Okay. So similarly, there are many molecules of I negative are produced in this mechanism as we are using 4 molecules of HI with one molecule of phosphorus. So again, there is homolytic fission of this CI bond because this CI bond is weak in nature due to the high size of iodine. As iodine has large size, the bond formed between the carbon and iodine will be weak because there the carbon have 2p electrons and the iodine have 5p electrons. So there will be poor overlapping of the orbitals. So it will undergo homolytic fission. Again, I negative is attacking on this radical. Okay. Now the carbon have a single unpaired electron. We will call it a radical. When this iodine negative, I negative will attack on this radical, then this there will be generation of a negative charge on this carbon. Wait a second. Yeah, this is your structure. CS3 group, CS3. So again, when iodine gives its electron to this carbon, there is formation of a radical. Okay. This carbon is getting a electron from iodine, then it will acquire negative charge that is anionic in nature. Then the last step is attack of H positive at this position. So attack of H positive as in this reaction H positive is also produced as the source of H positive is HI as we are using hydrogen iodide. Yeah, it is also known as hydroiodic acid. Here, so finally you will get the product as alkane. So this is a mechanism by which you will get alkane as a final product. So, so this is the one different reaction in which the reagent used is red phosphorus and HI. Here, yeah. So today we are done with our reduction reaction. In reduction reactions, we get aldehyde alcohols from aldehyde and ketone using nickel, palladium, platinum as catalyst in the presence of molecular hydrogen and using some other reagents such as sodium borohydride and lithium aluminium hydrides. The second one is reduction to pinacol, but in the presence of alkali amalgam. The third one is reduction to hydrocarbons. The first among these, the first is Clemenson reduction, in which the reagent used is zinc amalgam in the presence of HCl. And the second one is Wolff-Kishner reduction, in which the reagent used is hydrazine Ani instead of using any alkali amalgam or transition metal amalgam. Here, the last one is the reduction action with hydroiodic acid with phosphorus. So this is the all about reduction reactions. So if you like my video, then please watch and share it and subscribe my channel.